Hello, this is a video on the EM algorithm. It's going to be a two-part series where the first part is a little more theoretical and showing why the EM algorithm works, and then the second part will be examples illustrating how to do the EM algorithm. Here we're going to assume that we have some observed data, and then we have and that's X, and Z is a latent or missing data. We do have a probability density or a probability mass function if they're discrete, and the likelihood is just, it's the same thing, but thinking about the parameters as variables versus the actual variables. And this, anyway, so the goal is to find the MLE, the maximum likelihood estimator, of theta, which is our unknown parameter, over the observed data only. See here with the Z complicates things because we don't know what it is. It's unknown. And so what the EM algorithm does is it takes our joint density, or I'm gonna call it, I'm gonna work with the probability mass function. So it takes our joint probability mass function, sums out the Z's, which gives us this, and then we're going to maximize this in the likelihood function to find the likelihood, here, the MLE for theta, and that's a semicolon, not a J. The E step is in the EM algorithm is we take the expected value, and I'm going to go in detail of where all this comes, where it comes from. I just want to explain what the EM algorithm is, and then we'll get into a proof, and all this will make perfect sense when I'm finished. So here the E step is we're going to take the expected value over our missing data. So it's like we're averaging over our missing data of the log of this likelihood. And that we're going to call that Q. Okay. So, and the theta T is our initial guess for our parameter, and in the EM algorithm we have to have an initial guess, and then each step improves that initial guess. So then the M step is we take our Q that we just found, the expected value, and then we maximize it over all possible theta. And then that value is our new theta. Call it theta T plus 1. And then we use this as our estimate for theta. And we repeat the M step with this value. And then we repeat the E step with this value. And then we repeat the M step with this new value to come up with the T plus 2. And here's something that I sometimes goes overlooked. Argmax versus just max. So if we want the maximum of this function, we're actually finding the value, the highest value of this. But argmax means we're finding the theta that maximizes this. So this takes on a biggest value somewhere. And where does it take on that biggest value? That's the theta, that's the argmax, so we're trying to find that. So one note, the EM algorithm improves this Q function, and improve means makes it larger, makes it bigger. And this is rather than the probability mass function, and the log of that anyway. But we'll show that improving this, or making it get bigger, implies that this gets bigger. And to maximize this, that's the MLE, to find the theta that maximizes this. Well, that I'm going to show that it's equivalent, that whenever we make this bigger, then we make this bigger, meaning finding a theta that improves this. And it's pretty fascinating. So let's just go through each step. So let's assume that the probability mass function for our missing data, given our observed data and our parameter, is positive. And we do that because we're dividing by that value. So this here, the numerator, is the joint distribution of our data. That's what we said right here. And then this is, and if you think about it, if this is probably A and B, then that is equal to the probability of A times the probability of B given A. Anyway, so that, anyway, you can think about that little simple probability to come up with this. So we have this here, and if we take the log of both sides, then we get the log of this, and the log of a division is the difference. So that's what this is. Then we're going to take the expectation of both sides with respect to z given x theta t. And remember, theta t is our first guess at theta. Okay? Well, in our expression here, there's no z here. There's a z here and a z here. So if we take the expectation of a constant, we just get it back. So this comes down, but these have expectations. And so we need to sum over all possible values of z. And so this piece is here. And then this is the density, or the probability mass function, that we're taking the expectation with respect to. So then we'd bring this down to here, and then this is the probability mass function. And this is just the definition of expectation. You take the value, you know, what we're taking the expectation of, and then take it times the probability mass function and sum it over all values. Okay. Well, this first part here, we are going to call Q, and that's what the literature calls Q. Okay. And then this second piece we're going to call H. Okay. Now this is true for all theta. Okay. And including if we set theta equal to theta t, this relationship is still true. Okay. So if we repeat this step, so what that means is here we put, instead of theta, we put theta t, and then we take the expectation in regards to this value. We're going to get the same thing back, except for instead of using theta, we use theta t. So here's theta t. So these two functions are true. Then if we take the difference between 4 and 5, that's what this means right here, we get this value, the difference of those. Okay. So here, I'm just going to call this quantity asterisk, and we'll come back to this, and we'll show that asterisk is non-negative, and this is we'll use what's called the Gibbs inequality. You can use different proofs, but I think the original used Gibbs inequality. So if this is positive, that means this piece is less than that, which is what it shows here. Okay. Well, note that if, you know, when we do this, the M step is maximizing this in regards to theta. Okay. So this is our initial guess right here, and then we take this and maximize it. So we're going to choose the theta, which increases this, and it maximizes. So this piece is always bigger than this one. So we get that this piece is positive, which then, since this is positive, meaning greater than or equal to 0, then it says that this piece is greater than this piece. Okay. Well, this is what we want to maximize. So we take our initial guess, and if we take one step and make it bigger, which is what this does, because this is bigger than that by this inequality. So by making this bigger, so we derive this in the expectation step, and then we maximize it, we get that, it's positive, which then this implies that we're really maximizing the log of the likelihood. Okay, so then Q increases the log likelihood. Okay, and that's essentially how the algorithm works. Now that's a very glossy, argument over this, but one note is when we get this function, how do we maximize it? Well, you take the partial derivative, set it equal to 0, and you solve. That's one way. There's Newton-Raphson methods. There's a whole slew of different ways to maximize this. Okay, so the one piece that we needed to prove was that asterisk was positive. And if we can show that, then the EM algorithm is shown to always improve the log likelihood. So here's Gibbs inequality. If we let P and Q be probability mass functions, then this quantity, has to do with entropy, which we won't discuss much here, is always less than the cross entropy. And these two quantities are only equal when each of the outcomes, or PI, is equal to QI, and that's for every I. Okay, so this is Gibbs inequality. So let's show this. Step one is that note that the log of x is always less than or equal to this linear function x minus 1. I'm not going to prove it. You can look it up. Now, initially we only want to take the I in a set, capital I, where the set I makes the PI's positive. Okay, so then we take this quantity, which is very close to our inequality that we want to show, is equal to this. So this is the log of a quotient, is the subtraction of those. Then, because of our step one here, this inequality, we can plug it using this, we get this, it's less than or equal to this. But then when you multiply the P in, we get this inequality. Okay, so now note that I'm saying it's positive, and the reason is that I is in the set, the entire set that makes each PI positive. So this is 1. Now the QI, these I's may not include all of the QI. So this quantity will often be less than 1. So you're taking a 1 and then subtracting something that's 1 or less, that's going to be positive. Okay, so that says that this quantity is going to be greater than that. But then that says that this relationship is true, taking the negatives, which is what we wanted to show. Okay, but it's a little tricky because we only looked at the set that I is in capital I. Capital I made the PI's positive. Okay, so when we need to expand over the other values of QI, which may mean that these PI's are 0. But to have a PI 0, you can't take the log of it because that's negative infinity. And so expanding this to all values that pi, may be 0 is a little bit tricky. We're skipping that step, but essentially it's a definition. So here, anything times 0 is 0. And when you expand this to the i's that aren't in capital I, and here what they do is they just create a definition that this, you just essentially call this 0, and then it's true. There's some technicalities in there, but we're going to wash over that. Now, if we let pi be this and qi be this quantity, that's exactly this h and h minus h, where the h theta t. So this is always positive by the Gibbs inequality. Anyway, so that means maximizing the Q function is equivalent to maximizing the log likelihood. Anyway, hope you enjoyed it. I'm going to go through some examples in the next video, and I'm going to be very specific on each step and how it all works. If you like the video, hopefully you subscribe and like it, and I will see you in part 2.